Hey.
So let's restart with the lecture for this afternoon on group theory. So it's the second lecture of this tutorial series given by Professor LUIZ Cansado from UFMG.
Hey. Good afternoon. I'm back. Okay, so yesterday we went through some overview, okay, about the basis of group theory. I showed you how to construct a character table, how to read a character table, and now I will treat like real systems. I think Graphene is very simple to understand, and I will pick Graphene as an example, and also because I know it very well. Most of things here I took from my PhD thesis that was quite a while ago. Okay, so let's see here. So this is the crystal lattice of graphene. Here the atoms are okay, let me. I put two different atoms here, but the atoms are all carbon atoms in graphene, so they should be the same. This is the first Brillouin zone. It's also hexagonal. It's important here to see the high symmetry points, okay? This is the gamma, K, M, T is this line between gamma and K, and sigma is this line between gamma and M. U is something, is a general point inside. This is actually the T prime, this is T, okay? So these are the high symmetry points and directions in the Brillouin zone. U is just a general. Okay, so which symmetry we have for graphene? This is six-fold symmetry, okay? This is kind of obvious. We have a six-fold axis, which if we rotate this by 60 degrees, this atom comes to this atom comes to this, and then, so this is a six-fold symmetry, okay? We have some planes here. If we get the unit cell of graphene, okay, I'll do this with my, since I'm using the mouse, I think this will be easier. You go faster. No? Okay, so this is the mirrors, okay? This mirror here brings this atom to this atom and the opposite and the other way around, okay? We have another mirror here, which is this mirror, okay, in this direction, and another mirror in this direction, okay? They all, this is, okay, this is a vertical mirror, and we call this another family of vertical mirrors here. We call this, I call it diagonal mirror, but we have like two families of mirrors here, vertical mirrors. We have two families of C2 axis, okay, perpendicular to the C6 axis. We have C3 axis, okay, and okay, let me show everything we have here. We have inversion symmetry as well. If this is an inversion point, okay. We have horizontal mirror. We have glide planes in auto-reflection planes that you do reflection and then you can rotate back. So all the symmetry operations of graphene brings to the D6H, and the pathway is quite simple. If we take here, let's see here our schema which I showed yesterday. We have a Cn axis, which is n larger than 1. This is a C6, is the largest order axis in graphene, okay? This is a C6, okay? We have more than one C3 layers. If you, okay, here's the thing. We have C3 layers, okay? And then we also have what we call the C2. We have n C2 prime layers, okay, perpendicular to this Cn. We have 6 C2 prime axis, okay, perpendicular to the C6 axis. And we have a horizontal mirror. We go to the D6H group. These are the matrix representation of all operations. We have the identity, C3 axis, we have C2 axis, C6, and so on. All the mirrors. And then I showed you yesterday how to build these matrices. And this is the character table for the gamma point. This is the point group for graphene, okay, D6H. If you get the space group, is this group here, D6H1. This is number 191 in the crystallographic tables, or international tables, okay? All right. So we have all these classes. We have the identity, C3. We have a C2 layer perpendicular to the graphene. We have the C6 layer. I'm naming layer what is axis. So C2 axis, okay, perpendicular to the graphene. We have the C6 axis. Then we have these two different groups of C2 axis that we can just rotate the graphene in the plane like this. We have the inversion. We have the rotor reflections, like reflection and then rotate C6. We have the horizontal mirror. We have rotor reflections with the C3 axis, and then we have all these families of vertical mirrors, okay? All right. So this is the group, this is the character table. What we do with that? I told you yesterday, Raman, so if you want to do optical spectroscopy, vibrational spectroscopy, okay? First of all, you have to look at the base functions, right? And I told you yesterday, those irreducible representations that have quadratic functions, okay, they are candidates for Raman. So they can represent vibrational modes which are Raman active, okay? And I told you that if you have like representations that transform like vectors, okay? For example, Z or XY, they are candidates for infrared activity. But we have to be careful because we also have the acoustic modes, which also transform like this. So, okay, let's do this analysis here, how we build this. You see here that I have a few lines, which I call this the equivalence representation. I will explain this. This is the atomic site representation. This is the lattice vibration representation. This is the Z representation. This is the pi electron representation. Okay, these are all important for this analysis. Okay, if you want to do vibrational analysis, you have to understand the normal modes, okay? The normal modes, they carry the symmetry of the network. So the first thing you want to see is the atomic site matrices and the phase factor matrices. Okay, the atomic site, let me see if okay. The atomic site matrices, matrix, it's very simple. You have a matrix which the basis is the atomic sites. So we have two atomic sites in the unit cell of graphene, right? We have this one here, and we have this one here. So the identity would be just 1, 0, 0, 1, right? Then you do the symmetry operation, and you see if you exchange 1 and 2 or not. If you exchange 1 and 2, okay, you change the sites. Then the diagonal terms, they flip. So, okay, if it's 1, 0, 0, 1, then it will become 0, 1, 1, 0, because you exchange 1 and 2. So here's the thing. What you want is to build these atomic site matrices. And it's just a matter of seeing if you exchange atoms 1 and 2 or not. For example, if I do a 6-6 rotation, okay, the black atom comes to the white, and white comes to the black. So I exchange 1 and 2. Okay, so these matrices will be 0, okay, 0, 1, 1, 0. And what matter is the character of the matrices, which is the sum of the diagonal terms. So if you exchange sites, the character will be 0. If not, the character will be 2. Okay? So here we go. If I take the, like for example, the identity, it doesn't change anything, it's 2. The C3 doesn't change because, it's 120, so it goes to the same side. But this C2, it changed. The C6 exchange sides, so it's 0. Okay, so this is the characters of the atomic site. But I'm doing the equivalent here. Why? This is not important for the gamma point, because the phase factor is 1 for everybody. But it is important for other points inside of the Brillouin zone. So when we do this atomic site analysis, if we are in the gamma point, this is okay. But if we are analyzing a symmetry outside of the gamma point, there's a phase factor, okay? And this phase factor matters because you are modulating your network with that phase factor. Then we have to calculate the matrices, which is the matrix of the phase factor. What's the matrix of the phase factor? We have to build these matrices here, and we have the exponential of T1 times scalar k. Okay, T1 is the vector that brings the atom back to the original site. So you do the symmetry operation, and then you calculate the vector that brings that atom back to the same site. For example, if I do C6, okay, this atom here, atom number 1, comes to the site number 2. The vector that brings it back is this vector here, okay? If I do, for example, C2, it goes here, the vector will be this one. All right, so this is the vector T1. And then I have the vector T2, is the vector that brings the atom 2 back to the original Vyckoff position, all right? And K is the wave vector of the point of the Brillouin zone which you are doing your analysis. If you're doing like just zone center, it's gamma, so the K is 0. Okay, so it's important that you take all the operations and then you calculate what's the position after. Then, okay, we have the Vyckoff positions here, is the original position, and then you calculate what's the position after I apply the symmetry operation. Then you build all these vectors here. And then you calculate which vector would bring that atom back. Okay? Then you can calculate of course, for gamma point, everything is 0. Okay? So all the exponentials will be 1. But I will come back to this point in a while. But the important is that the equivalent matrices are the matrices that are the product between the atomic site matrices and the phase factor. So it's not just the atomic site. The phase factor also matters. Okay? This is kind of hidden in the literature because most books, they treat very well the point symmetry, which is like in the gamma point, the center of the Brillouin zone, because it's for molecules. But for crystals, okay, this is usually at the end of the book, and this is kind of hidden there. Okay, so for the gamma point, what we have is the equivalent matrices, okay, which is here. And then what we do for lattice vibrations, which representations are associated to the lattice vibrations. Okay, let's go. What we have to do now is, once we know what is the equivalent representation, and how do we know this? Okay, we calculate the matrices, then we know the characters of these representations, okay? The characters are here. So everything that I build is a linear combination of these functions here. This is a space, okay, and these are my vectors, okay. These are the base vectors of my space. And everything that appears here is a linear combination of these guys. So I have to do a projection and see what's the linear combination of these representations here that would give me these numbers here. And is, for example, for the equivalent representation, is the gamma 1 plus the gamma 1 plus gamma 3 minus. So it's this one plus this one gives me this guy here. Okay, so let's go to the, since we already have the equivalent representation, we can do the lattice vibration. The lattice vibration will be the vector representation, which we know is the x, y, and z. So it's the linear coordinates, okay? And the direct product with the equivalent representation, okay? So what's the vector representation? We have here z, and we have here xy. Xy is a two-dimensional representation. So, and if I do the sum of these two rows here, I have the vector representation, which is, as I told you, gamma 2 minus plus gamma 5 minus. Then I have this here, all right? Sorry, this is the this is the vector representation. Now, the direct product between these two rows here give me the lattice vibration representations. And what I have is, this is a sum, direct sum. This is a linear combination of gamma 4 plus gamma 6 plus gamma 2 minus and gamma 5 minus. All right, let's understand this here. This is the lattice vibration. This for the, okay, I'll just give a break now. This was for the gamma point. So I understand which representations, okay, are associated to the lattice vibrations in the gamma point. What is that? The normal modes of vibration at the gamma point, okay, they are associated with these symmetries, okay? So some will be gamma 4, some will be gamma 6, and so on. Okay. This is for the gamma point. But the normal modes, they can be modulated. So you have normal modes with all kind of wave vectors. Then you can calculate this for all points inside of the Brillouin zone. Here I have the K point, here I have the M point, the T point, the E point, and so on. They do not have the same symmetry as the gamma point. They have lower symmetry. Then it brings to the what we call the star of K. Here. So the gamma point has the C6 symmetry, okay, six-fold symmetry. The K point doesn't have the same symmetry because these two K points here, they are not equivalent, okay? So the K point is equivalent to this K point here, but it's not equivalent to this K point here, okay? The graphene is a little bit weird. This is not a Bravais lattice, and the K points, this one is similar to this, is equivalent to this one, and this one to this one, but this one is not equivalent to this one. So what we do is we build something which is called the star of K, and the star of K for the K point here would be a star like with the three-fold symmetry. So the K point has a three-fold symmetry. So it lowers down the symmetry of the system. So the K point has a D3H symmetry. I'll show this. The M point doesn't have this three-fold symmetry. It has a two-fold symmetry. And the T point also. So when we build the character for all the points in the Brillouin zone, okay, you have to understand which symmetry that point has. So the gamma point carries the unit cell symmetry, okay? It's six-fold. The K point is in the corners of the Brillouin zone with the three-fold symmetry. So this is the symmetry of the K point. The M point has a two-fold symmetry. This is the M point. It has a two-fold symmetry. For example, you have to bring the M point here. Okay? This is the equivalent M point. It's here and here. Sigma point also has this is a CS symmetry. You just have like a C2 axis, sigma horizontal, and a vertical mirror. And then you go down with the symmetry until you go to the U point, which is any point inside of the Brillouin zone, which you have two basic symmetries, is the identity and the horizontal mirror, okay? So you go down with the symmetry, and you have to understand the phase factors for these guys. So you can build the equivalent representation, you can build the vector representation, and you can build the lattice vibration representations for all points inside of the Brillouin zone. It's basically the same as the gamma point. The difference is you have to understand the symmetry of that point in the reciprocal space, and you have to be careful with the phase factor, because now the K will be the coordinate of that point inside of the Brillouin zone. Okay, so for example, we got all those lattice vibrations at the gamma point, okay? Then we got, if you remember, we got like gamma 5, okay? But gamma 5 is a two-dimensional representation, and we have gamma 2. They all transform as X, Y, and Z. But then we go to graphene, how many vibrational modes we have at the gamma point? How many degrees of freedom? 6. We have 3 times 2 atoms, okay? But 3 of them are just translations. These are the acoustic modes. So they have frequency 0. They have 0 frequency, okay? The other 3 are optical modes. Gamma 6 is a 2-dimensional representation, okay? Is double degenerate here at gamma, and we have this other one, which is this gamma 4, okay? It's an out of plane. This guy in graphene is silent. It doesn't have any basis function, okay? And the gamma 6 has a quadratic base function. It's Raman active. So graphene is boring. We only have this very strong band, which is the stretching, okay? Is a very high frequency band, okay? Which is a double generated mode here, okay? And it's kind of easy to calculate the Eigen Vectors. It's out of scope here, but we can calculate the Eigen Vectors with geometry, okay? Some algebra, we can calculate the Eigen Vectors. The Eigen Vectors are actually here for these normal modes. The acoustic modes, they just move, okay, in one direction. And we have the vibrational modes here. Again, this guy here is silent for graphene. Okay, so we calculate and we do the assignment for the gamma point. How do we do for the other points? It's not trivial, but we can do what we call correlation. Okay, when you go down with the symmetry, okay, that guy doesn't disappear. It just goes down with the symmetry. So there are some correlations. What do I mean? Is, for example, this guy here, K2, is a part of something that was in graphene, okay? The K point doesn't have the same amount of kind of symmetries as in graphene because we have less operations, but everything can be projected, okay? You just lower the symmetry. It's like here, if you see here, this branch doesn't disappear, but obviously this branch changed the symmetry because you break it's not degeneration anymore. So what we do is with some algebra or just looking at the character tables, okay, which character is kept for that specific, okay, operation. You can map inside of the Brillouin zone how these symmetries go, okay? For example, for this guy here, this longitudinal optical phonon, okay, which has gamma 6 symmetry, it goes sigma 3 or M2 or T3 and so on, okay? This ITO is quite important. It has a second order band. So it goes like sigma 1 and then go M1 and so on. Then we can, from the gamma point, if you follow, okay, this correspondence, you just follow the symmetries inside of the Brillouin zone. Then if you do your job at the gamma point, assigning all the symmetries at the gamma point, which is not difficult, okay, you can map inside of the Brillouin the whole thing. Okay, the other thing which is important for optical spectroscopy is to understand the electronic part, because you have to understand the electronic transitions. Then we go out of the lattice vibrations and we go, for example, for graphene, the whole thing happens in the optical spectrum with the pi electrons, okay? And the pi electrons, they have this orbital here, the Z orbital, okay? perpendicular to the plane. And what's the base functions for this orbital here? It's just z. This z is the function. Then what's the symmetry of this p orbital? Is the symmetry of the z, is the representation that is assigned to z, the basis function z, times the equivalent representation. Okay? Okay. Here. Then we have the, which one is z? Is the gamma 2 minus. Okay? Is here. And what's the equivalent representation? Is gamma 1 plus gamma 3 minus. Then if I do the direct product between these two representations here, I will find, okay, the representation for the p electron, which is gamma 4 plus gamma 2 minus. So now I know which is the symmetries of these two branches. Okay, so this is the electron dispersion curve around the Brillouin zone of graphene. Okay, one of them is gamma 4, the other is gamma 2. Which is which? I don't know. So then we need to do some first principle calculations. Okay, I know that one is gamma 4 plus, the other is gamma 2 minus, but I don't know which one to pick. And I know from first principle calculations that the pi band is gamma 2 and the pi star, which is the conduction band, is the gamma 4. At the gamma point, okay? This is at the gamma point. And then I can map the whole thing again, doing the same process as the lattice vibrations. For example, I have the K point, I can calculate the P, the pi, represent the characters at the K point, and then I know it's like a K6 symmetry, something. Okay. Yesterday we talked about symmetric and non-symmetric groups, okay? And I comment here that I would give an example. The graphite is a non-symmetric group. This is the graphite structure, okay? We have this plane here, and we have a very equivalent plane here, but this is what we call A-B stacking. They are mismatched. They don't match. Like the plane, the A plane here is displaced from the B plane. Okay, one of the atoms of the A plane go to the center of the hexagon of the B plane. Okay, so there are some consequences. This is the unit cell of the graphite. So graphite looks very symmetric, but the unit cell is weird. We have these two atoms here, and we have these two atoms here. It's like if we draw this thing here, these two atoms are the atoms of the unit cell, but they are not in the same plane. Okay, the symmetry, the operations are the same. Okay, the elements are the same, but the operations are not the same. So the symmetry elements are exactly the same. We have inversion, C6, C3, all the C2 axes, and so on. But they don't work the same. Look at here. If I do C6, just a C6 is a six-fold rotation. The white atom comes to the gray position here. But they are not in the same plane. So that cannot be. What I have to do now is to make a translation, okay, of half of the lattice parameter around Z. So if I rotate and make a translation, then I put everything back. So this is a non-symmetric group because some of the operations need a translation, okay? then we represent in this way. This is the way to represent. The matrices are the same as the point group for graphene, but we have some operations. For some operations, we have to make a displacement, a translation. For example, the C6, we have some, the sigma vertical. This is kind of obvious here. For example, this operation here, this mirror, also brings this atom here. But they're in the different planes, so what you do is like this. Then you have to displace everything. Okay? So this is a non-symmetric group. We have the same point symmetry operations. We have the same symmetry elements, but we need translation for some of them. Okay, it's the same. You see here, this number, this 6H is the same. So the point group is the same. But the space group is not, because we have this translation. Okay? So it's not the same. That group of graphene, I think is 191, and this is 194, the crystallographic table. Okay? We have these translations. Okay, but everything is done same way. Now we have the translation, but the calculations are basically the same. But now we have 4 atoms, okay, not just 2, in the unit cell. Okay, we have these 2 atoms here, and these 2 atoms here. Just an example, the dispersion curve looked very much the same, but it's still like, it's kind of degenerate all around, okay? And then we can build, again, the lattice vibrations at the gamma point. We have more now. Now you see here. We still have the acoustic. They are always there, okay? But now we have many more vibrational modes, okay? We have twice. Then 3 of the base functions that transform like the linear coordinates are the acoustic modes. But now we have also some associated with the infrared. Okay? For example, this gamma 2 minus here is this OTO2 here. Where is it? This guy. Okay? This guy also have the symmetry of the Z component. This is an out of plane mode. It's basically this mode here. Okay? This guy is infrared active. These are the where is it? Yeah, this one is the acoustic out of plane, Z, and this one is the infrared active. Okay. All right. This is then graphite. We can map inside the whole Brillouin zone. Same way, you do these correlations and you go, if you know the gamma point and you calculate all the character tables and all the equivalency representations and everything, you don't have to know the assignment inside of the Brillouin zone. You have to know the assignment at the gamma point, and then you do all the correlation and you can map the whole thing. Pi electrons, same way, okay? Then we have here, but now we have twice, okay? We have 2 dispersions in the valence band. We have 2 dispersions in the conduction band, okay? And this is just at the plane, okay? Because the Brillouin zone is also 3D. I'm just looking at the middle. And we can also assign this, the electron, the pi electrons, which are also Z. As I showed you, this gamma 2 minus here is a Z component. Okay, so if you want to see more about the group theory of graphene, this paper is quite complete. Okay, then we jump inside of the title of this this mini course here, which is group theory of 2D materials, because I showed you now a monolayer and I showed you bulk, okay? So I showed you graphene, one layer graphene and bulk. But we have more. We have 2 layers, 3 layers, 4 layers, and so on. And what's the difference? There's a basic difference, okay? Usually, if you go from even and odd, the symmetry is changed. You have to be careful. So if you do 1 layer, this is odd number of layers. If you go for 2 layers, it's usually different. And then if you go more, it becomes probably is odd and even, and so on. Okay.
So yesterday, I'm going back to this point group, space group, and symorphic and non-symorphic. Are you using space group as a synonym for a non-symorphic group?
Yeah, if you, okay, this is a good question. When you use the space group and then you use the point group, okay? If you don't have any translation, okay, you can just go to the point group symmetry for the gamma point. And you go to other, and you go to the other points, okay? You can go to the point group of those guys, okay? But you have, like, even for the space groups, you don't have to stick with the point groups. This is the thing, okay? But you can use the point group symmetry for non-symorphic. It's okay. I mean, it's a simplified way to write things.
So, but my point is, non-symorphic group and space group in your language is the same.
No.
But then I don't see the difference because they both have translations.
No, you have space group for everything. You have space group for everything. You have space groups that are symorphic, and you have space groups that are non-symorphic. Okay?
What is a space group that is symorphic?
It's a space, okay, I think he has a very clear.
Okay, so I was Carlos' student, so I know his doubts. Sorry. So the idea is that a symorphic group is one at which all relevant translations are block translations.
Okay,
so block translations are trivial. You can always neglect them when you calculate the factor group. So what happens is that once you have a space group from which you can factorize all block translation, then the resulting factor group is a point group, and then you work with the point group always. In some groups, you have translations that are not block translations. They are fractions of the block translations. In these groups, you cannot factorize these fractional translations, and these are the non-symorphic groups. And one more important thing is that at the gamma point, the block phase is always 0 because k is 0. So at the gamma point, trivially, all non-symorphic groups are isomorphic to a point group. So if you are working at the gamma point, forget about this distinction. It's always a point group.
Perfect. That's it. But still, in the crystallographic answer, okay, even for non-symorphic groups, you have the space group for that thing. You have a space group for everything, okay? But this is perfect. You see, for example, for the graphite, the translation that we have here is half C. Of course, everything has a C translation. If you do any operation, then you do the C translation. That's what he saw. He told us. This is a block translation, then it's okay. All right? Good. Okay, so here's the case of graphene. All right? that we have a monolayer, and then we have a two-layer graphene, and the symmetry is changed, okay, from monolayer for two layers, and it's basically very similar to what we have for graphite. If you go from monolayer to this guy here, but look at the two-layer graphene. We don't have the translation in Z. Okay, so this is like a two-dimensional thing. You cannot rotate and make a translation because we go to the empty space. So you don't have the possibility, okay, to have this translation around Z. So in case of bilayer graphene, if you make a rotation here from this atom to this atom, it doesn't work. So you lose the C6, and you lose all those operations in graphite that you need the translation. So you lose the six-fold symmetry in bilayer graphene, and you go to the three-fold symmetry, okay? And this happens for everything that is even, but we still have the C6 for the monolayer, but you still have this guy here for the C3 for the odd, okay, and for the infinite you can make this translation. So then you have the possibility. So in this paper, then we start to have like for even modes, for even number of layers, for odd number of layers, or for infinite number of layers, okay, or for monolayer. Then, for example, this paper here, we have all the lattice vibration representations calculated for monolayer, or we have for any number n even, or we have for any number n odd, okay? And we have the pi electron wave vector point group representations inside of the Brillouin zone, and this is for everything inside of the Brillouin zone. Then this comes to the boring part of the talk here, because it's the most interesting part if you're doing research. But of course, these are just like results, okay? What you do with this? You go to the character table and you say, okay, this is like, for example, we have the pi electron representations for every point inside of the Brillouin zone for monolayer graphene, even number of layers or odd number of layers inside of the Brillouin zone. Then if you look, okay, for the optical transitions, for example, along this high symmetry line T, okay, you can calculate the selection rules for these optical transitions. For example, we start here with this T2 symmetry, okay, and we have the T4 symmetry for the conduction band, okay. If you want to make a dipole transition, okay, from initial state to the final state, okay, and you have some light polarized in some direction, okay, you will represent the polarization vector of the light with some symmetry of how to say, some coordinate symmetry. So for example, you say, okay, I want to make a polarization around X, okay? Then you go to the character table and you look at the representation that is for which the base function is around X, is the vector X, okay? So for example, X belongs to the T3 representation, okay? Then what happened here? I want to go from T2 to T4. In terms of symmetry, okay, I have a T2 symmetry, and I will apply light, okay? The polarization is along the X direction, so it has a T3 symmetry, And then I'm going to the T2, sorry, I'm going from the T2 to the T4, okay? If I do the direct product between these three symmetries here, the result is non-null, okay? It means that a transition is allowed. It means that the oscillator strength is strong for that transition. No, it means that it's not zero. Okay, so this is a possible transition. What I just say here is, I can go from this point here, one electron here can be excited to the conduction band here if I apply light polarized along in the x direction. Okay, I just do the direct product between the representations. Okay, and I see that the result is not zero. But for example, if I use T1, and T1 is the representation for the y direction in the T point. So for the x direction is okay. For the y direction, the representation is T1. Now if I make the product between the T4, T1, and T2, they do not connect. So the result is zero. So it means that to bring an electron from here to here, or to make an electron hole pair here, I cannot apply the light around y, okay, in the y direction. This is forbidden. It means that it's zero. Yes, it means it's zero. It's not possible. It's that question that you made yesterday. Somebody, I think was you. One make this question yesterday. So it is prohibited. Then this is how it works. And you can make more complicated things, or you can just like see how the optical transitions go, or you can see how the Raman process go. And for example, we can calculate from the base functions which Raman modes we have for an even number of layers, which Raman modes we had for odd number of layers, which infrared modes, active modes we have for even number of layers, and so on. Okay, we can calculate more different things, like for example, double resonance process, like second order Raman bands. Okay, this involve phonons. Then we can put the phonon symmetry. Okay, and then we go like, for example, to T2 to T2, T4 to T4. This is like you just follow the pathway. Okay, you want to go from, yeah.
I have a question. So I will be naive. All this sounds
every question is naive,
dandy and good, but the issue here, I mean, I don't know whether this makes sense or not, but all these assumes that the atoms are in those positions, but atoms are always moving.
Yeah, that's
and they are
true.
vibrating. So all this symmetry breaks, isn't it?
Yeah, you're right. There is some, but I mean, this is the adiabatic approximation, right? So the atoms are just steady state. But I mean, I think you're right, but the amplitude of these motions, they are so small, okay, that you do not change the symmetry of your system just by moving, okay?
Mm-hmm.
So the motion is really, really small. And you know, you are in the gray area. This is not like, what I mean is, you're right, but then you go, yeah, exactly, so small the change, okay, which the rules is still okay.
Apply. Okay.
Yeah, and we can ask for the theoretician. Things are not really moving in the ambient conditions. The phonon population is really small. This is another point, but. Mm-hmm. Yeah, sure. Yeah, but at the end, things you have an average, and of course you are in a gray scale there, but the symmetry is kept
Thank you.
overall. Okay, but I want to just finish here. My time is going down, is going to finish. But the thing is, you can follow, okay, the pathway. Okay, you go from one electron branch, and then you make this dipole transition. Okay, you can see if they connect by making the product between these two symmetries and the photon symmetry based on in the direction you are doing the polarization. Then, if you want to make like if it's Raman, then you have a phonon transition from one point to another point. Then you can make again, okay, this product. So you just make the matrix elements, okay, and you see the Hamiltonian between them. And then you go like, okay, so what's the function of this initial state? And what connects to the final state? And what's the operation? So what's the symmetry of the Hamiltonian? And then you go, okay? And then you just see if the whole thing is possible or not. Okay? I hope I gave you at least a glance. This was an example of graphene, and tomorrow I go finally to the TMDs and the phosphorine. Thank you.
Do we have any further questions? Actually, I have a question. So, why does it change the symmetry when you go to a gated graphene? Because basically, I would imagine that it's just shifting the bands downwards, so the transitions would be the same.
It's because, yeah, but it's because when you apply gate,